Welcome to section 1.1, Definitions and Terminology. Objective number 1, determine a differential equation. A differential equation, DE, is any equation that contains derivatives. One of the most well-known differential equations is Newton's second law of motion, which states that if an object with mass m is moving with acceleration a and is acted upon by force F, then F equals m times a. So F is the force, m is the mass, a is the acceleration. But if this is one of the most well-known differential equations, where are the derivatives? Well, in order to express the equation as a differential equation, we need to reframe it slightly. So recall that acceleration a can be expressed in one of two ways. It can be expressed as the derivative of velocity, so that's dv over dt, or it can be expressed as the derivative of position, so that's the second derivative of u over the second derivative of t. So here v represents the velocity of the object and u is the position function of the object over time t. Additionally, we should remember that the force F may depend on time, velocity, and or position. So with these considerations, we can express Newton's second law as a differential equation in terms of either velocity, F, or position, U, as follows. So in the first one, we replace the acceleration for the derivative of velocity, and in the second one, we replace acceleration for the derivative of position. Now, our formula for Newton's second law of motion is written as a differential equation. Here are some other examples of differential equations. We have the first derivative in the first equation, the second derivative. I believe we then have the second derivative, first derivatives in the third, first derivatives in the fourth, and then the last two show our partial differential equations in the first order and second. Objective number 2, classify a differential equation by type, order, or linearity. So we can classify differential equations according to their type, order, and linearity. Classification by type. So the first type of differential equation that we're going to look at is the ordinary differential equations, or the ODEs, and these contain only ordinary derivatives of one or more unknown functions with respect to a single independent variable. So in these four examples here, we have one or more unknown functions with respect to a single independent variable, and in these cases it would be dx. The ordinary derivatives would be written by either the Leibniz notation or the Lagrange prime notation. The second type of differential equation is the partial differential equation, or the PDEs, and these contain partial derivatives of one or more functions with respect to two or more independent variables. So here you see in both of these two examples we have partial derivatives, and they are then respect to two or more independent variables, and in these cases it's the second derivative of x and the first derivative of x, or partial derivative of x, my apologies. The second way that we can classify differential equations is by order. And so the order of a differential equation, and this can be either ODE or PDE, so ordinary or partial, is the order of the highest derivative in the equation. So if you remember back in algebra, think of order as the power of a polynomial. So the order is going to be the highest derivative that's represented in that equation. So let's classify each of the following differential equations. So we're going to determine what order they are as well as what type of differential equation they are. So as we look at this first one, we have dy over dx equals e to the power x minus 5. All right, and so our derivative here is dy dx, and this is a first order differential equation. Now, is it an ordinary or partial? Well, this would be an ordinary differential equation. The second equation, all right, we have a second derivative in our first term, and then in our second term, we have a first derivative. So our highest order would be the second derivative. So we're going to have a second order here. And this too would also be an ODE as it contains no partials. Our third equation is written in a different notation. However, we can still identify that our highest derivative here is going to be y prime. So that would be a second order differential equation. And because there are no partials, this too is also an ODE. The fourth, we have a term here that contains a power of 4. So it's the fourth derivative. All right, so this would be an order of 4, fourth order. Since no partial derivatives are present, this is an ODE. All right, our next one, we have a first partial derivative. All right, and so this would be an order of 1, and it's a partial derivative, so it's a PDE. And then in our last equation here, we have a second partial derivative and a first partial derivative. So the second would be our highest derivative. So this would be a second order PDE. Next, we are going to classify our derivatives by linearity. Okay, so whether it's linear or nonlinear. So a linear differential equation can be written in this form. And what's important to note in this form is that the dependent variable and all its derivatives are always to the first power. Okay, so they're not raised to a second power, third power, fourth power. They're always to the first power. The second thing to know is that there are no products of the function y and its derivative. Okay, so nothing contains y and the derivative of y in any of the terms. And then the third thing to note is that the coefficients can be 0, constants, or functions of t. In this formula would be functions of x. Okay, so a nonlinear differential equation is a differential equation that's not linear. So as long as your equation satisfies these three things, then you have a linear differential equation. If they do not, then it would be nonlinear. So in this exercise, we're asked to determine the order of each differential equation and then determine if it's linear or nonlinear. So in our first example, we have y minus x times dx plus 4x dy equals 0. Now, this isn't written in an explicit form, and we'll learn more about explicit shortly. And so I'm just going to rewrite this so that I can identify the order of this differential equation. And so to do that, what I'm going to do is I'm going to divide everything in this equation by dx. And when I do that, I will get y minus x plus 4x times dy dx equals 0. In this format, I'm easily able to identify the order and then hopefully determine whether it's linear or nonlinear. So in this new format, I know that this is a first order DE. More specifically, it is an ODE. All right, but I believe all of these are ODEs, so we'll just stick with the order for today. Now, I need to determine, one, if the dependent variable and all its derivatives are all to the first power, which they are. Two, there are no products of the function y and the derivative of y, and that's true. We do have a coefficient here, or a constant here, that has y, but it's not being multiplied to the derivative of y, so we're okay. And then the coefficients can be 0, constants, or functions of x, and that is all true. So this is linear. Okay. For the second one, we have y double prime minus 2y plus y equals 0. Okay, I believe this probably was supposed to be prime. Okay. All right, so for our order, our highest derivative is the double prime, so that would be an order of 2. Okay. The dependent variable and all its derivatives are all to the first power, so nothing here is being squared or cubed and so forth. The function, so there are no products of the function of y and its derivatives, nothing. And then the coefficients can be 0, constants, or functions, and they are. So this is linear. Okay. For the third one, we have x cubed times the third derivative y over the third derivative x plus x times dy over dx minus 5y equals e to the power x. So the highest order here is this third derivative, so that would be the third order. Okay. Dependent variable and its derivatives, all to the first power. There are no products of the function y and its derivative, and the coefficients are either 0, constants, or functions of x, and that is all true. So this is linear. Okay. Number 4, we have 1 minus y times y prime plus 2y equals e to the x. So the highest derivative present is this y prime. So we know that this is a first order differential equation. So now let's go through our 3 points to determine whether it's linear. So first one, the dependent variable and all its derivatives are always to the first power. Yes, and that's true. There are no products of the function y and its derivative. Well, that's not true. We have a coefficient here that depends on y, not x. So the coefficient depends on y. And so this one does not satisfy the 3 points for the linear equation. Okay, so the coefficients can be 0, constants, or functions of x. However, this coefficient is dependent on y and not x. And there are no products of y and the derivative of y. Okay, so again, 2, this does not hold for being linear. Number 5, we have the second derivative of y over the second derivative of x minus sine y equals 0. Okay, and so the highest derivative in this, oh, we didn't write nonlinear here, nonlinear. Okay, so the highest order in this differential equation is second order. Okay, and this differential equation is not linear because sine y is not a linear function. So non-linear function. So this is going to be a non-linear differential equation. Okay. All right. Number 6. So the fourth derivative of y over the fourth derivative of x plus y squared equals 0. So the highest differential equation the highest derivative of this differential equation is the fourth derivative. So this is going to have a fourth order. Okay, now we need to determine whether it's linear or nonlinear. Okay, and we have y squared. And the first point in order to be linear is that the dependent variable and all its derivatives are always to the first power. And we see here that this is not a power of 1. So this is a nonlinear DE. Okay. Objective number 3, verify a solution to a differential equation. So a solution to a differential equation is any function that satisfies the differential equation on a given interval. So the interval on which the solution of the ordinary differential equation is defined is called one of these 4 things. You're going to see this throughout this course. It could be called the differential of definition, the differential of existence, the interval of validity, or the domain of the solution. And it can be on an open interval, a closed interval, an infinite interval, and so on. All the different combinations. So in our first exercise for this objective, we're asked to verify that the indicated function is a solution of the given differential equation on the given interval. Okay, and so for our first example, we have the derivative equals xy to the power 1/2, and then we have our function y equals 1 over 16 x to the 4th power over the given interval from -infinity to infinity. Okay, so when we're asked to verify something like the indicated function is a solution to a given differential equation, the first thing we need to do is plug the function into the differential equation. But before we do that, we need to find the first derivative of this function. So the first derivative of this function, so if we take y equals 1 over 16 x to the 4th, and we take the derivative of y, we are going to get 4 over 16 x to the 3rd. If we simplify this, we get 1 over 4 x to the 3rd. Okay, so now let's take the function and plug it into the differential equation. Okay, so we know dy dx, which is the same thing as y prime, equals xy to the 1/2. Well, dy dx, according to our indicated function, is 1/4 x cubed. And then we know y as 1/16 x to the 4th raised to the 1/2 power. Okay, so in order to plug in the function into the dE, which is the first step, we needed y and we needed y prime, or the derivative of y. And so we had to find y prime first before we can take that function and plug it into the given differential equation. And so now we can simplify. So this is 1/4 x cubed equals x times 1/4 x squared. So you'll take the power and distribute it. And so then we would have 1/4 x cubed equals 1/4 x cubed, which is true. Okay, so we then show that both sides of the equation are equal. Okay, so that's the second step that we did. So the third step now is to confirm that the solution works in the given interval. So is it true that from -infinity to infinity that dy equals x times y to the power 1/2 on the indicated function y equals 1/16 x to the 4th? It does. So thus, y equals 1/16 x to the 4th does satisfy the dE, and hence is a solution. Okay, let's do another example. So we have y double prime minus 2 prime plus y equals 0. So that's our dE, and our indicated function here that we need to verify as a solution is y equals x times e to the power x over, oh no, I should say -infinity to infinity. All right. So in order to plug in the function into the dE, I need y, y prime, and y double prime of my indicated function. So I know y is x e to the x. So y double prime, so I have to take the derivative, y prime, before we go to double prime. Got ahead of myself there. Y prime would be the derivative of x times e to the x, which would be x e to the x plus e to the x. Okay, so we would have to do the product rule there. So then we would take the derivative of y prime, and so we would then get x e to the x plus e to the x plus e to the x. So if we simplify that, we will get x e to the x plus 2 e to the x. Okay, so now we then need to plug the function into the dE. So we had y double prime minus 2y prime plus y equals 0. So y double prime is x e to the x plus 2 e to the x, then minus 2y prime, which is x e to the x plus e to the x plus y, which is x e to the x, which then equals 0. Okay, so now we can simplify this. So we have x e to the x plus 2 e to the x minus 2x e to the x minus 2 e to the x plus x times e to the x equals 0. We can combine like terms, and so we will have these terms that are like. So x e to the x minus 2x e to the x plus x e to the x equals 0. And then we have 2 e to the x and then minus 2 e to the x, which equals 0. So 0 equals 0. Okay, and so 0, so knowing this, is this true over the given interval, negative infinity to infinity? Yes. So our solution, thus y equals x e to the x, does satisfy the dE, and hence is a solution. All right, let's go to another one. Okay, so 4x squared y double prime plus 12x y prime plus 3y equals 0. That's our dE. Then our function, y equals x to the power negative 3 halves over the interval 0 to infinity. Okay, so we have our function y equals x to the power 3 over 2. And in order to plug that into our dE, we need y, y prime, and y double prime. So y prime, so first derivative of y, would be negative 3 over 2 x to the power negative 5 over 2. Then we have double prime y. So then we have negative 3 over 2 times negative 5 over 2. That will be x to the power negative 5 over 2 minus 2 over 2, so minus 1. That would simplify to 15 over 4 x to the negative 7 over 2. Okay, so now we have y prime and double prime of y. So let's plug this into the dE. So that's 4x squared y double prime plus 12x y prime plus 3y equals 0. So that is going to get us 4x squared y double prime 15 over 4x to the negative 7 over 2 plus 12x times negative 3 over 2x to the power negative 5 over 2 plus 3 times x to the power negative 3 over 2 equals 0. Oof. All right, let's do some simplifying. So we have 4 times 15 over 4, and then x squared and x to the negative 7 halves. So that's going to get us 15 x to the negative 3/2, because 2 would be 4 over 2. And then 4 minus 7 is minus 3. Then we are going to have plus 12 times negative 3 over 2, and then x and x to the negative 5/2. So that's going to get us a negative number. So that would be 6. So negative 18. And then this is 2 over 2 for the 1. So that's minus 3 over 2 for the power of x. And then we have plus 3x to the negative 3 over 2. I'll write that down here as well. Simplifying as we go. All right, and so all of these have the variable x with different exponents. Oh, sorry, all the same exponents, not different exponents, all the same exponents. And because they have all the same exponents, we can then add all the different coefficients together. So that's 15 minus 18 plus 3. So in other words, 18 minus 18 equals 0. Okay? All right. Now, does this satisfy over the given interval? And our given interval here is 0 to infinity. All right? And it does satisfy on 0 to infinity and not like from negative infinity or any other which way, because we are dealing with powers. And not just any powers, fractional powers, which means we're dealing with roots. And anytime we go into the negative space for inputs, we then are dealing with imaginary numbers, all right, which does not exist in the real. So, thus, y equals x to the negative 3/2 does satisfy the DE, and hence is a solution. Okay. Objective 4. All right, determine a solution to a differential equation. So this should say 4. The graph of a solution of an ODE is a solution curve. So since the solution is a differential equation, it is continuous on its interval of definition. Thus, there may be a difference between the graph of the function and the graph of the solution. For example, the domain of y equals 1 over x, considered simply as a function, is the set of all real numbers x except for 0, which we know. But if we have a condition where y of 1 equals 1, then this image here would be our solution, okay? Because this right here is the condition, okay? It is the part of 1 over x that contains the condition y of 1 equals 1. And it's on the interval of existence where x is between 0 and infinity. Okay? So a solution in which the dependent variable is expressed solely in terms of the independent variable and constants is said to be an explicit solution. An implicit solution is just a solution that's not in explicit form. Okay? So for example, the relation x squared plus y squared equals 25. And if you didn't know that that was a circle, it is, with a radius of 5. This is an implicit solution of the differential equation dy over dx equals negative x over y on the open interval -5 to 5. By implicit differentiation, we obtain the following equation. And then through simplification, we can get 2x plus 2y over dy dx equals 0. Okay? This equation, when simplified, or I guess if you were to solve for dy dx, you would get the differential equation dy over dx equals negative x over y. Okay, so that's how the two equations correlate. So if you take x squared plus y squared equals 25 and apply implicit differentiation, you get this differential equation. Okay, so now when we solve for y in terms of x, so if we go back to our relation x squared plus y squared equals 25, okay, and we solve for y, we are going to get this solution. Y equals plus or minus the square root of 25 minus x squared. And this is in terms of x. So the two functions, y equals positive square root 25 minus x squared and y equals negative square root 25 minus x squared, satisfy the relation x squared plus y squared equals 25 and are explicit solutions defined on the interval -5, 5. Okay? So visually, our relation x squared plus y squared equals 25 is an implicit solution. Okay? Then we have two explicit solutions where our relation is written in terms of x on specific intervals. So -5 to 5. Okay? So in this exercise, we're asked to verify that the indicated function is an explicit solution of the given differential equation. Assume an appropriate interval I of definition for each solution. Okay, so here we are given our differential equation and we're given our explicit solution. Okay, and now we need to verify that it is a solution. So it's very similar to the problems that we had just walked through, except for now we have an explicit solution. Okay. All right, so first thing that we need to do in order to plug in our function into our DE, we need to find our prime and our double prime, because in order to get our double prime, we're going to need our prime. Okay, so let's first start off with y. So y equals negative cosine x natural log secant x plus tan x. Okay, in order to find y prime, we are going to need to use the product rule. So I'm going to let u equal cosine x, and I'm going to let v equal the secant x plus tan x. Okay, so u prime is negative sine x, v prime is 1 over secant x tan plus tan x, times secant x tan x plus secant squared x. Okay, so that's the natural log of secant x plus tan x. And then this simplifies to secant x times tan x plus secant x all over secant x plus tan x. Okay, so what I did is I distributed out a secant x between these two terms, which left me with tan plus secant x, which will allow me to eliminate those two parts, leaving us with just secant x. Okay, so then y prime equals minus sine x, and this is going to be in parentheses because I have to multiply it by my v, which is the natural log of secant x plus tan x plus cosine x times secant x. Okay, so that's y prime. So now y double prime is going to be, let's write this over here, y double prime. Oh, let me flip this here. Well, before we do that, actually, let's distribute this negative in the front. I completely forgot about that. So we'll have sine x times the natural log of secant x plus tan x minus cosecant, or not cosecant, cosine secant x, which if we simplify is actually 1 over cosine, but for these purposes right now I'm just going to keep it as cosine secant x, just because we still have to take its derivative again to the second derivative. Okay, so next we have to take the second derivative. So let's continue on. All right, so we are going to get, when we take the second derivative, cosine x times the natural log of secant x plus tan x plus sine x secant x. Okay, so I'm doing the product rule again, but I have all the information that I already need right here. I already did it. Remember, we're using the product rule. Okay, so let's simplify this some more. So this would equal cosine x times the natural log of secant x plus tan x, and then sine x times secant x is tan x. Okay, so now we can take our y and our y double prime and substitute it into the differential equation. So here we have y double prime plus y equals tan x, I believe. Yep. So y double prime is the cosine x times the natural log of secant x plus tan x plus tan x. Y is the negative cosine x natural log secant x plus tan x. Okay, and so what we have here is two terms. Let me get a different color so you can see it. Two terms that cancel out. This term and this term. They cancel. And this is equal to tan x. Need to include that. And so we're left with tan x equals tan x, which is true. Okay. Alrighty. So a solution of first order differential equation containing a constant c is a set of solutions called a one-parameter family of solutions or general solution. So a single differential equation can possess an infinite number of solutions corresponding to an infinite number of choices for the parameters. So in this next exercise here, we're asked to verify, so we're doing the same process we've been doing this whole lesson, to indicate that the family of functions is a solution of the given dE, and then of course assume an appropriate interval of definition for each solution. So we're just going to assume that it's on an interval of definition that works for this function. Okay, so let's first start off with what we need to know. So we have dy dx in our dE, and so we need y prime. So we are given y, and y is 2x squared minus 1. Oop, that didn't go well. Let's erase that real quickly. There we go. 2x squared minus 1 plus c1 times e to the power 2x, negative 2x squared. So y prime. So we take the derivative of the first term. That would be 4x. Derivative of negative 1 disappears. And then we take the derivative of the third term. So we would have, let's do a plus, take the derivative of the power. So that would be negative 4x. And then our constant, and then e to the negative 2x squared. Okay, so that would be our y prime. So now we can substitute it into our dE. So our dE is the derivative of y over the derivative of x plus 4xy equals 8x cubed. So dy dx is the same thing as y prime. So that would be 4x minus 4x ce to the negative 2x squared plus 4x times y, which is 2x squared minus 1 plus ce to the power negative 2x squared equals 8x cubed. So let's simplify the left-hand side a little bit. So we have these terms already done. Then we can distribute this 4x, so that's 8x cubed minus 4x plus 4x ce to the negative 2x squared equals 8x cubed. Then we can combine like terms. So that 4x here and minus 4x cancel out. And then we have this large term and this large term that cancels out. And so we'll have 8x cubed equals 8x cubed, which is true. So we have verified that the indicated family of functions is a solution of the given differential equation. And remember, it's a family of functions because we have a constant c there that could represent a set of solutions. Okay. So a solution of a differential equation that is free of parameters is called a particular solution or an actual solution. So in this exercise now, we're asked to find the values of m so that the function y equals x to the power m is a solution of the given differential equation. So we have 4x squared y to the power n plus y equals 0. And we want to find the values of m for the function y equals x to the power m. So in order to take this function and substitute it or plug it into our DE, we are going to need to, oh yeah, this n is supposed to be double prime. I needed to tell you that, not n, double prime. Into our DE, we need to find y prime and y double prime. So we know y equals x to the power m. So y prime would be the derivative of that, which would be m times x to the power m minus 1. So y double prime, or the derivative of y prime, would be m times m minus 1 times x to the m minus 2, because I would be subtracting another 1. So now that I have all of the equations I need, I can substitute it into my DE. And that's not what I wanted to write. Let's erase that. So y double prime plus y equals 0. So we have 4x squared times y prime, which is m times m minus 1 x to the power m minus 2 plus y, which is x to the power m equals 0. Okay. We can simplify. So we have 4x squared and x to the power m minus 2. They have the same variables, and we're multiplying them so we can combine their exponents. So that would get us 4x to the power m. So it's 2 plus m minus 2 is m. Then we can simplify m times m minus 1, which would get us m squared minus m plus xm equals 0. Both terms have a term of xm, so I can factor out an x to the power m, because they both have a factor of that, which will give us 4m squared minus 4m plus 1, which is 0. Then if I factor that, I would have 2m minus 1 squared. If I set 2m minus 1 to 0, m equals 1/2, or nope, got ahead of myself there. M equals 1/2. Okay, so now that I know the value of m for this function, that is the solution of the given DE, y equals x to the 1/2, or the square root of x is a solution. Okay, so we found the value of m so that the function y equals x to the power m is a solution of the given differential equation. And in order for this equation to equal 0, one of those two factors have to equal 0. So if we set to m minus 1 equal to 0, we got 1/2. So if m is 1/2, then we know that equation will be 0 equals 0, making it true. So our function, the function that is a solution to the dE that we were given is y equals x to the 1/2. So up to this point, we have been discussing a single differential equation problems containing one unknown function. But often in theory, as well in many applications, we must deal with systems of differential equations. And a system of ordinary differential equations is two or more equations involving the derivatives of two or more unknown functions of a single independent variable. So in our last problem for this section, we are asked to verify one last time that the indicated pair of function is a solution of the given system of dE's on the interval -infinity to infinity. So now instead of just having one solution and one dE, we now have two functions and two dE's. However, the steps are still the same, all right? We are still going to plug the function into the dE, then show that both sides of the equations are equal, and then confirm that the solution works on the given interval. Okay? So our two functions are x equals e to the -2t plus 3e 6 to the power 6t, and then y equals -e to the -2t plus 5e to the power 6t. Okay, and so we need to find the derivative of both of those functions because the first derivative is present in both dE's. So let's do that. So we know that x equals e to the -2t plus 3e to the 6t, and y -e to the -2t plus 5e to the 6t. So let's find the derivative of x. So we take the derivative of the power. So that's 2e to the -2t. Then we take the derivative of this term, which would be 6 times 3, 18 e to the 6t. And so then we do dy dt, and then we will have, take the derivative of the power, so that's -2, so a negative times a negative is a positive, e to the -2t, 6 times 5, 30 e to the 6t. And so now we have the first derivatives of x and of y. So now we want to substitute them into the dE's that are given. And our first dE given to us is dx over dt equals x plus 3y. And our second one is dy dt equals 5x plus 3y. Okay, so let's substitute this in. All right, so we know that x, and I'm actually going to move this over. All right, so we want these two to match. Let me get this into a different question. We want these two to be the same, and we want these two to be the same after we substitute into our equation. So we have x, which is e to the negative 2t plus 3e to the 6t plus 3 times y, which is negative e to the negative 2t plus 5e to the 6t. So we'll have negative 2t, 3e power 6t minus 3e negative 2t plus 15e 6t. So then we have like terms. So we'll have negative 2e to the negative 2t, so that's these terms. And then we'll have plus 18e to the 6t, and that's these two terms. And this equals dx dt. So now let's do dy dt. So we have 5 times x, which is e negative 2t plus 3e 6t plus 3 times y, negative e negative 2t plus 5 e power 6t. We need to distribute so we can combine like terms. So 5e to the power 2t plus 15e to the power 6t minus 3e to the power negative 2t plus 15e to the power 6t. So then we can combine like terms, and we'll have 2e to the power negative 2t, so that's these terms. And then we'll have plus 30e to the power 6t, and that's these two terms. Okay, and this expression equals dy dt. Okay, so the pair of functions that were given to us right up here are solutions to the given system of differential equations. Okay, awesome. That concludes the end of section 1.1. Enjoy.